Howdy, everybody. Hope you're doing well wherever, whenever you are. We are here for day 2 of Advent to Code. Today was a fun day, I think. Nothing particularly hard to solve. Sorry, I'm on the wrong screen here. Uh, I don't think it was particularly crazy. Again, I think it was a relatively easy day. Um, why do I say that? I think even if you just read the problem as is and went through it naively, you could probably still solve the problem. Even if it maybe took you a while to understand how to solve this, you you could just kind of brute force it is the way to say. And I mean, to be honest, my solutions are essentially a brute force. I do have, if you look right here, I have like kind of a semi-optimized solution that I'll show you that will kind of like give you an idea of what it looks like. Um, uh, some other way. And I actually think there's other ways to do this just because like it's possible that like the set of numbers that you iterate over is like pretty small. And so again, the n size is small. In fact, I think I actually did it right. It's like 1.5 million total numbers that you're like looking at. And so however you solve it is potentially really easy, especially if you parallelize it. So anyway, we'll get into that in a second. Just a couple of housekeeping things before we get started. Someone talked about starting a leaderboard, so I have created one right here. I will add it to the description. I'll try and remember to add it to the description. Feel free to join in. Show me how much better you are than me. I mean, my times are terrible, right? Part of that is because I had to get up early, right? 5 a.m. The odds of me being awake when Advent to Code releases during my day is basically zero. So I'll definitely be behind on the times wise, but I'd love to see your times if you're staying up and solving it. I'd also especially love to see your code, right? Like a part of what I want to make this is learning and growing. And obviously I'm learning from you guys. Hopefully you're learning from me. And so when you post a solution, for example, right here was an example of someone who um, posted their solution, and I think it was a cool solution. In fact, I would argue that the solution, because of the size of the input, is potentially better from like a readability perspective, even though it's like not the quote unquote most optimal solution. And I don't want to like pick on anyone. Because my solution is almost certainly not optimal either. I'm sure there's ways that you could make mine faster, but it's literally just like saying, oh, I'm going to move the dial one tick at a time, and I'm going to, am I going to go backwards or forwards based on left or right? And I'm going to keep ticking, and I'm just going to check, does the start ever get move past the 0? And if it does, I'm going to reset it to the original position. Or to the correct position, and then keep decrementing or moving around, and then you can track the clicks. And I think this is a cool solution, again, because it's readable, right? And it's not like this solution is suddenly going to take 15 minutes to run, right? It's still running in like milliseconds, if not microseconds. And so I love that they went with, this is day 1, it's a simple problem, I can make my solution readable, I'm using variables that are readable. So I think that's just something to think about. Like, that's why I love reviewing code, because it gives me these ideas of like, so when I was in school, part of my like dissertation thing was comparative analysis of programming code and languages. And so I think about this a lot, like, how do you deal with readability? How do you deal with writability? Where does the confluence of the two come together and like make for a good language? But also, like, how does it look, right? Like, you don't want to come back 2 years and say, like, how did I even solve this problem, right? This one is interesting in this way because you can read the you don't even have to read the problem, and you could read this code and kind of understand what's going on. This one potentially you could not, right? My solution right here. Sorry, this. I guess I'm not zoomed in, huh? Sorry, I'm not zoomed in, so if you didn't see that, here's their code, which I think is, again, very readable, very approachable. This is potentially not, right? Like, if I were to come back to this in like 2 years, I'd be like, what even is this, right? Maybe I would read it, it'd be more readable for me, just because, like, this is more my style, more functional approach, filtering, scanning, the REM Euclid I'm familiar with, so it would make more sense. But for other people, it might not, right? And so you might argue that, like, this itself is less readable. Obviously, you can go about fixing that in different ways, right? Add more commenting. I think I did a better job commenting part 2 than I did part 1. Part 1 doesn't have any, so anyway, those are just things to think about, and this is all for me to say. I love reading your solutions, so feel free to join the leaderboard. Totally own me on times, but most importantly, I'd love to see your solutions. So send me your solutions. I love to read through them, kind of get an idea. One of my favorite parts is after we've solved the problem is to go look at them. So anyway, with that, let's get on to the problem. So what is this? Somehow there's a gift shop at the North Pole, which they mentioned doesn't make sense, and I agree. That kind of doesn't make sense. But what they say is, one of the elves find you and says, "Hey, can you help me out? I have a bunch of product IDs, but some of them are invalid." And so they're going to give you a list of ranges to check, and you want to check whether or not it is invalid. And by invalid, it would be if, at least for part 1, if the sequence of digits is repeated twice. So that is to say 55 works because it's got a 5 and then a 5. The easiest way to think about this is you take the number, split it in half, and are the two halves the same? Like, that's what it's asking. So this is correct. 64, 64. 123, 123 is correct because you split it in half and they're both the same. This one is not because there's no leading digits. 101 is not. And you could imagine a bunch of numbers. 15 is not, obviously, because 1 and 5 are not equal. So that's what you're trying to do for part 1. You're going to be given a range of numbers, and you need to go through that range and figure out which ones are invalid and which ones are not, sum them together to get your answer. I don't think this one was too hard. I mean, I just did the string solution. I'll show you the int solution. Again, one of the first things I did was, how many numbers am I dealing with? And because it was only 1.5 million, I'm like, oh, I can parallelize that and solve that in microseconds. You could do other solutions, including, like, I'll show you the int solution later. But so what do I do for part 1? Well, we're working with ranges. In the past, I've created my own ranges for, like, reasons that, I mean, maybe weren't helpful or were. But in this case, I think we can actually use the ranges that are in the Rust standard library. So that's what I do. Our parse function is going to return an iterator of ranges of usize. So all I do is I split by comma, I trim, remember, trim the new line at the end. You don't have to do that when you call lines, like that's something that I've come to realize. Input trim lines, the trim can be omitted, but input, if you get a single line, you definitely want to trim the new line at the end if it happens to be there. Anyway, we're going to split by comma. Excuse me. We're going to split by comma and then split the commas by dashes, and then we're going to map those to a range. So here's us just creating a range, right? So we parse unwrap the both sides, and then we do the dot dot equals. This has the effect of creating our range, and it is inclusive, right? We have the first digit and the last. The default range operator, just to be clear, like what we're basically doing is like 1 dot dot equal 10. This is going to produce like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. Whereas if you did 1 dot dot equal 10, we'd only be getting like these two numbers. This is just to be clear, like we're doing inclusive versus exclusive. Have I mentioned this before? My family once had an argument about pick a number between 1 and 10. Like, is it inclusive or exclusive? And we were getting so loud that at a restaurant that we realized people were staring at us, yelling about inclusive or exclusive. Pick a number between 1 and 10. Anyway, this one is inclusive, so we want to be inclusive. Actually, so how do we solve part 1 then? Now that we've parsed it, I mean, it's pretty easy, right? As we just say, get our ranges. I'm going to parallelize it, so I use parbridge here, right? I already have an iterator. I'm gonna bridge it into a parallel iterator. This is just a rayon thing, right? So if I just use this is a rayon thing, and then I flatten it, right? So I'm gonna take my range and turn it into one number. This is actually an interesting thing. Order is important here. If you flatten and then parbridge, you can see the times are substantially worse. And why is that? Well, it's because like the solving a single value, like the number 22, does it meet the criteria of an invalid product ID, is actually very small. The computational complexity is very small. So if you parbridge this way, you're actually spending a lot of time like dealing with feeding values to your parallel processing. Whereas if we do it the other way, like this, now we're saying like, okay, for each parallel process, deal with one of the ranges. That happens much faster. And so you can see it solves substantially faster. Anyway, so that's what we do. We get our ranges, we parallelize each of the ranges, then we flatten the range, and then we just ask the question, is this specific value in the range valid? And or invalid, I guess I should say, because we're counting invalid ones. So we're gonna filter by all the ones that are invalid, and then we're going to sum those up, right? That's what the problem asks us to do. Well, how do you figure out whether or not both halves are equal? In this case, I did the string version of it, so you can see how the string version works. Basically, we turn the number to a string. If it's not divisible by 2, obviously they're not the same. Actually, now that I think about it, this is not strictly necessary. I presume we get the same answer. It's slightly slower because now we have to do the split at a couple times, but think it's, on the order of the same one or the other, right? But this is just an additional check. Obviously, we want both sides to be equal. So if a string is length 9, it's impossible for it to be, quote unquote, invalid or match the criteria of the puzzle. Otherwise, we just split at that half mark, right? So we say, okay, split the string in half, give me a left and right, and then we ask the question, are the left and right equal? There you go. That's it. That's it for part 1. Again, I think there's definitely optimizations we'll talk about later, but I opted for the string solution for the initial part, and I think it was just because it's easier to reason about. It's not like quote unquote optimal, but I think it's a totally fine solution. And I think if you go with the string solution, I'm sure there'll be people on the internet that say, well, actually, there is a better solution. And there is better solutions. There's always better solutions. But, if you're trying to solve it yourself and this is how you solved it, I think that's awesome. That's great. That's how I solved it. So what happens in part 2? Well, they say, not only do we want you to split it in half, but can you find any repeated segments of size n where n is at least 2? So what are they saying? Like the previous solution still works. So if you split it in half and the 2 are equal, that still works. But what if you split it into thirds like this and those 3 are equal? Now that works as well, right? So you can see the 1 2 3 1 2 3 is repeated 3 times. The 1 2 is repeated 5 times here, and the 1 is repeated 7 times here. So in all these cases, you're able to say, hey, give me a chunk of the string, like some n size of the string, and break it up, and are all of the chunks equal? So like the smaller digit doesn't change, it's still this one. But like where's one? This one right here, right? So this range has a 5 6 5 6 5 6, whereas in the previous puzzle that would not have been the case, right? So um anyway, so what are you doing now? Maybe the way to think about this in part 2 is you're saying, oh, there's some additional logic here. Not only do I want to split it in half, but I want to split it in thirds, fourths, fifths, and so on until I've reached half the size of the string. And I just keep doing that and saying, are all of those parts equal? Does that make sense? Anyway, so how do I solve this for part 2 then? Again, we're still par, bridge, and flattening, and we check each value. We're going to sum. But our criteria changes a little bit, right? So we say turn it into a string. And now we're going to count from 1 to 1/2 the size of the string, right? So if the string is 8, we're going to start at 1 up to 4 inclusive. And we're just going to check. We're going to do the same check, but we're going to do it for that size, that prefix length. And so obviously we need to divide equally again, right? But this time we're not by 2, but by d, right? So is it divisible by 1, 2, 3, 4? And then we say we're going to get the prefix of that size and repeat it some number of times. So this repeat operator is pretty cool. You can, given a string, you can say repeat the string some number of times. So ABC repeat 4 will give you 4 ABCs. That's exactly what we want, right? So we say, given a prefix, if we repeat it lane over d times, how many does that have to be lane over d? Yes, because it could repeat, like, we've broken it into, like, we're getting chunks of 4, but we want to repeat it however many times you can do 4 chunks. And we say, is that equal to the original string? Then if it is, that one counts, otherwise it doesn't. So we're going to try that multiple times until we find a solution. If we don't find a solution, we return false. So, like, just to be clear, the way the logic works is, oops, I have it right here. Like, say we have a number, 1 2 3 1 2 3. We're gonna start at 1, and then we'll do 2 3 and 4, right? No, so divided by 2, so we won't actually do 4. We'll do 1 2 and 3. These are the values for d, right? These are the d's we're going to check. So 1 is going to be just going to return the value 1. And so we're going to do 1 repeated 6 times. So 1 2 3 4 5 6. And are they equal? No, they're not. Bad. Now we're going to do it 2 chunks. So we say the first chunk is 1 2. So we're going to go 1 2 1 2 1 2. Are they equal? No. Bad. Now d is 3, so we're going to grab the first 3, and so we're going to go 1 2 3 1 2 3. Are they equal? Yes. Yay! So that one does work. However, if it didn't work, it fell through, we would fail. That's the algorithm. That's all we're doing, right? And that's what gets you the solution to part 2. Now, I will say there's an integer way to do this. Again, I think this is totally fine. If you look at the solutions, I'm streaming, so these take about like twice as long as they normally would. Like, I think normally these solve in, like, well, you can see here, like 5 seconds. And so it normally takes, or 5 milliseconds, I should say, 5 milliseconds to run. And again, it's just because you're doing 1.5 million tests. So you're converting 1.5 million integers to a string, and then you're doing some of this logic. Still, because we can parallelize it, we can make this solve pretty fast. Well faster than, I think for Advent to Code, they've always said, like, you should be able to solve it within a couple seconds. Like, on some very basic hardware, right? You don't have to have the latest, just some basic hardware. You should be able to solve it in a couple seconds. So we're well within that range. There is an integer way to solve this though, and I'll show it to you. Again, we're still going to do the same thing. We're going to parallelize it, flatten it, filter by the ones that are correct, and then sum those up together. We just have to do something slightly different, and this is just for part 2. It works for part 1 as well. Part 2 is a little bit more complicated. The way the integer version works is we can figure out how many digits there are in the string, or in the number, I guess I should say, because it's not a string anymore. We can figure out how many digits there are, and then we can do the same loop, right? We're going to try 1 to digits divided by 2. This is the equivalent of getting us our length of the string. And then we go through that and we say, okay, go from 1 to half that, right? And check those and see if we ever get to we still need to equally divide, so that doesn't change. So if the digits aren't a multiple of d, we want to kill that. But then and we still want to get the prefix, and then we're still going to repeat it, and we're still going to check if the repeated value is equal to the original value. The thing is we just do it in a mathy way, a numbers way, instead of like a string way. So how do we do that? Well, here's the hacky way to get the number of digits. You just do I log 10 plus 1. Oh, I should mention, like, if you look at the help for, this is not like adversarial proof, adversary proof or whatever, right? If you look at the input, you assume the input's going to have valid ranges, and the ranges are going to be sane and things like that. So notably, none of the values are going to be 0 here, right? We do an I log 10. If it was 0, this would panic. So if you're worried about unwrap gate, my solutions aren't a good example. But this just has the effect of counting the number of digits, and the way it does it is, if you do an I log 2, it kind of tells you like how many of the digits are, how many of the digits are, or how many of the binary values are used, right? The numbers in the binary equivalent are used. And then you can do some funny math to get an I log 10, which tells you, based on the I log 2, here's approximately how many digits would be used in the 10-digit equivalent. And then you just add 1 to that. It's a funny hack trick that if you've seen it before, you just say, oh, I'll just have to remember that. I log 10 plus 1 works. Again, it doesn't work with 0. So it will crash if it's 0. So you just have to make sure your test is okay. But otherwise, this will give you the number of digits. So that's the equivalent of, checking the length of, getting the length of the string. So then how do we get the prefix? I think we've shown this before in other problems. Obviously, we want to get like the some chunk of the digits, and so how do we do that? Well, if we divide this number by 10 to the power of the number of digits we want, that has the effect of like shifting to just get those values that we're interested in. So the idea here is digits minus d. So we have like, say there's like 8 digits and we want 2 of them. 10 to the 2, we divide by 10 to the 2. That's going to like strip off all the digits but the prefix that we're interested in. So now we just repeat that for the number of times. Notice how we're doing digits divided by d here, and we're repeating the len, which is equivalent to the digits divided by d. We're still doing the same thing. We're just going to fold these values together to like recreate what the expected value would be, right? And how do you do that? Well, you take your current value and you times it by 10 to the power of d plus the prefix. So this 10 to the power of d has the effect of shifting 3 numbers this way and then adding the prefix to the beginning of it. if that makes sense. So once we've done those three things, that gets us here. Okay, I'm gonna draw this out. Look, I mean, you can see the code. It may boggle you a little bit, but I'll try and draw it out so it makes sense. Let's go back to our, well, what did we do? 1, 2, 3, 1, 2, 3. So we have 1, 2, 3, 1, 2, 3. How do I, what's a good way to represent this? Okay, we're gonna get our digits. We're gonna call the ilog. That's just the trick. So we know that the D, we're gonna do D, or I don't want to show this. We know the digits is 6, right? And so we're gonna go our D value. We're gonna go our D is going to be 1, 2, and 3. Those are the three ranges we're going to check. So how do we do this? Now we're going to do our prefix. And what this has the effect of doing is 10 pow digits minus D. So this is saying 10 to the power of the number of digits we have, 6 minus D, 1, 10 to the 5, right? So we're going to divide this thing by 10 to the 5. And that's going to have the effect of getting rid of these 5 and giving us just this 1. So now we're going to work with 1. And now we're going to repeat that 1 this many times. Like, so what does this do? In this case, we're doing 10 to the power of D, which is 1. So we're just taking the number, multiplying it by 10, and adding the prefix to it. Does that make sense what's happening here? So what we're going to do is it's going to be 1, and then we're going to do 1 plus 10, or no, 1 times 10 to the 1 plus 1, which is going to give us 1 times 10 is 10 plus 1 is 11, right? And now we're going to do it again, times 10 to the 1, right? Yep, times 10 to the 1 plus 1. So this is not a great example because, you know, this, now we're just doing 110 plus 1 is 1, 1. Let's do it for D equals 3, right? So we now have one, our grouping is going to be 1, 2, 3. And so now we're going to do that times 10 to the 3 plus 1. Well, what does 10 to the 3 have to do? Is basically we're putting like, oh, sorry, 1, 2, 3, right? 10 to the 3 is going to, what is this going to do? It's now going to shift this to be 1, 2, 3, 0, 0, 0. And then we're going to add 1, 2, 3 to it, which is going to net us 1, 2, 3, 1, 2, 3. And then we can just compare the numbers, right? So we say, is this equal to this, right? Yes, it is. And this one's not, right? So this one's bad. So no bueno. Does that make sense? I hope that makes sense. This is like these are just like math things that you can, if you've done puzzles before, I had to look these up just to be clear. Like, but when I say look them up, it's like, I'm like, oh, there is a math way to do this. 10 to the power of the number, you divide by 10 to the power of the thing. Like, think about what's happening here, maybe is the way to say it. Like, if you have a number like 1, 2, 3, 1, 2, 3, and you're dividing that by 100, right? That's going to get rid of these two values, and that's going to leave you with this, right? We're doing it by 10 to the, like, say it's 10 to the power of 3. That has the effect of like eliminating these 3 numbers and just giving us these 3 numbers, right? So once you've seen it a couple times, it kind of makes sense, and you're like, okay, 10 to the power of the digits minus D, that gives me the prefix. Now we just repeat the prefix by, 10 to the power of D plus the prefix, and then we can check if it's repeated. There's probably an even mathier way to do this. I just couldn't think of it. Like, in my mind, there were a couple times where I'm like, oh, is there some kind of binary representation that would make this? I don't think there is, because if you think about like the way I mean, my best guess is like if you could take these binary values and these binary values and say they overlap. I think you could, but like um so you could probably do some kind of checks like that. Is you could say you'd still have to do this math right here uh to get like this chunk, but you think about it as like you if you knew your prefix was 1 2 3, you would then go through all of them 1 2 3 1 2 3, these like imagine these in binary, right? So you go through each of these and you ask yourself, are those equal and are those equal, and if they are, then you've solved it. I think that way works too. um that's the closest I could get to like a binary solution. The thing that I was saying is like this number 1 2 3 1 2 3 is won't necessarily repeat in binary. So you can't just like take this number and like break it into chunks and say, does it repeat? It won't necessarily repeat with respect to this number right here, is what I'm saying. But you could potentially break the bigger number up and then do binary checks to say, are these numbers the same? That solution. So you can see what I'm doing is I'm just taking the repeated chunks and saying I'm rebuilding a repeated number. But what you could do is say, get this prefix and check, do each of the chunks of the actual number equal that prefix? That would also work too. I hope I explained that well. So anyway, that was the day. Not too crazy, I don't think. I don't suspect there's going to be a lot of problems with this day. Obviously, the number is large, so if your solution is slow, it might take a few seconds to run, right? Like I can imagine if I just done this with strings in Python, I probably wouldn't be solving it in 2 milliseconds. Um, but I still think you know, if you're solving it and it solves in a couple seconds, you're totally fine. Don't worry about it. Don't let the haters hate. Let's see. Okay, let's see how they solved it. TypeScript. Take the square root of the number, check fact. Okay, what factors? I may not be able to math a lot. Eventually realize that you only need to check 2 cases for any possible repeating sequences and can include any that fall in that. That I'm not aware of, so that would be interesting to know. Someone pleased. Oh, okay, and C without storing any numbers or iterating over IDs. Happy I could use them. IPOW. Num digits. Okay, so this is another way to count the number of digits. You just divide by 10 until your number equals 0. So eventually you divide and it equals 0. That gives you the number of digits in it. Also doing the power yourself. That's very cool. Sends the powers of 10 to k-fold repeats. Long are okay, I think this is the mathy solution. It looks like they are doing the mathy solution. They're just doing it in C. So this is, it looks like correct. Yeah, it looks like the way, a similar solution to mine. I still don't understand this, like, you only need small numbers, so just the most readable TypeScript solution out there. Bufflane input, split, reduce, start end for start end, ACK. Plus equals test. Okay, this is a JavaScript way to turn a number into a string. This turns it into a number. Okay, this regex does work. How cool is that? It's saying like, does some number of integers equal to that many plus more number of the capture group of this? So say you're looking for 1 2 3, it will first see, oh, does 1 repeat that many number of times, does 2 repeat number that many times. I have to give him that's a very cool solution. I now that I think about it, I presume other people may have solved it with regex, but that is a cool regex, right? So just to be clear, like what's happening here is they're saying try and capture some number of digits, 1 to n digits, and ask, does that repeat to the end of the string at least once? So very cool regex. Mine, here you go. Brute force solution. I'm sure it's fine. Don't overthink it. I think this is very brute forceable. Left, right. Bueno. Perfect. Yep. I mean, that's my solution in Rust. So, and divided by 2 plus. Yep. There you go. Okay. Perfect. Same thing. Oh, this may be obvious to people. Sometimes when I'm testing this stuff out, I want to like print out some stuff, but I actually don't want to print it out for the real problem. And it occurred to me the other day, oh, I can just do this. Config this. And it will print it out in the unit tests. So you see how it's printing it out in the unit tests, but it won't actually print it out in the solutions. I don't know if that helps anyone or not, but I actually found that useful, because sometimes when so like on this debug side right here, this side on the right hand side of the screen, I have a little thing that says run all the tests. Whenever a file changes, run all the tests and then run the actual main problem. And it's kind of nice to see those, but like what sometimes will happen is I'll want like 10 things from the test, but I'll get a million things from the actual solution. That doesn't help me. So like I'll anyway, that is neither here nor there. I saw the fumped print line, and anyway, very cool solution. I love Go. Fit in Spring to make more functional, but Rust is pretty. Here's the part 2. Check for repeating silliness. 1 input divided by 2 filter input lane. Yep. Any size 0 input lane step by size all block equal blah. Perfect. Oh yeah, this is a much more functional way to do it. So like ask yourself what's happening here, read it line by line. You're going to be given one string, so you're going to be given one of the values as a string, and then you say for 1 to the value divided by 2, or the lane divided by 2. So that's this part right here. Like essentially what they've done is they've taken this for loop and like gone even further. That makes sense. Then we filter where it's equally divisible. Is Clippy the only one that warns me about this? Clippy really wants me to use is multiple of 2, or is multiple of I in this case. But yeah, there you go. You filter, you always want to divide evenly in this case, and then say do any of those sizes. So you take the thing step by size, split the chunk, and say is it the same as the original chunk? Perfect. Well, in this case, you're saying, so like in this inner loop, you're say splitting by 3, for example. So you're saying all of the values, all of the chunks of 3 should be equal to the first 3. So, and is there any of these? Oh, so any of the length of the groupings that are all divisible by this, and you get your solution. Very cool. It is hard to stop doing things imperatively. It takes a lot of time, and I'm not perfect at it, so you can still see I did not do it. This one might be a fun one to go back. This one I did do more functional style, right? This one, I don't know how you'd make this one simpler, but like I think this part 2, definitely you could make it more functional like this. So very cool. MySQL. How is this even a thing? Holy cow. Okay. Let's see if I recognize anyone else. We already got lots of solutions. This is what makes it fun to look at. Ability first tried well, not fast, but things got it done. Yeah, a lot of string manipulation. I think that's cool. That's fine. This is totally, you can do it in a string. Just I thought it would. So here's the reason why I did part 2 in with the integer way as well. I want to get my reps in, and so I thought, ooh, can I kind of figure out how to do it the integer way? Min and max of each repeated group, then use the triangular numbers to compute these sums really quickly. The trick was to find the min max of each repeated group. Huh? There's some math thing that's not clicking to me. Okay, let's read this. Compute range sum. Compute range sum. Split by dash. Get the min, the max. Get repeated min. Repeated max. Range. Get repeated. I think there's some math that I'm missing here. Okay, another regex solution. Very cool. Another rust one. What do we got here? Validate similarity. Okay, so you tell it how much you want to split it, and for part 1 you're splitting by 2, right? You're always by 2. But for part go for K. I've never got used to using K as a variable, but it is a common one for these. Okay, so this is like a string solution, just slightly different. It is nice to have this in its own functional thing. Is like, does this do this? From a readability perspective, that might help too. Like, imagine this itself was a function, then I can just filter by that function, especially if it takes an integer. So that could definitely improve readability here, right? So there you go. Very cool solutions. Very cool. Okay, let's look at one more. Trying to look for some that I might know. Ooh, Haskell. Should we look at Haskell? Haskell? You little Haskell? Kamak Miller. Show. We split on comma. Some concat map isn't any repeats chunk length. Enum from okay. Yeah. Yeah, I think this is definitely just like a stringy way of doing it, right? And then you can sum up the values. Okay, very cool. Very Haskell. Almost. Sometimes it feels too functional for my liking. Did we get to some of the original solvers? Oh, here's someone from Everybody Codes that we saw some from. I prototyped the brute force since it was likely to work, but the final solution. The main speed up is only iterating through all possible repeating subsequence values rather than all values in the range. That has some minor challenges. When considering the repetition sequence of form 1, 2, 3, we're iterating over the first 3 digits with a multiplier of m. Oh, they're doing it in a new language, Odin. I think they were doing this. This person was doing it in Rust. I have not tried Odin. days. Fast parcel and read ranges. Okay. This is a more integery way, but it feels it's like 6 of one, half dozen of the other. The other thing you can do is count over, find how many digits you're at, and it looks like you're doing that. If you ever find a mismatch, it's the day 2 that I think is, or the part 2 that I think they're talking about is very interesting. I'll have to read this much more. Given a range is a to b, we can replace this iteration with a closed sum formula over x to y, where x is approximately a over m and y is approximately b over m. This needs 2 exclusions when processing a subrange of length L. If we previously processed lengths p of x, which divides. Oh, I see. So like, the you can think about like this number as like this number times like this number is the way to think about it. And so if you take this number and divide it by this and you get this, then you have then they're equal. Like this is a very much more mathy way than I would have ever solved it. That's very cool. Okay, let's look at a few more columns. I kind of want to get to some of the like speed solvers. Oh, perfect. Here we go. 2 minutes, 3 minutes. Video me solving brute force again. Just trial on part 1. Try splitting each number in half. Part 2, we try. Okay, so let's look at again. This is a very speed solving solution. So it's gonna look. It's not nearly as readable, but this person is a speed solver. So turn it to a string. Test all lengths. If it's equally divisible, lane x divided by k. This. Yeah. One. Yeah, you have to do this in your ranges in Python, right? You have to go plus 1. Two to lane x plus 1. Else 3. Oh, you only do it once for P2. Okay. I imagine during this, we won't watch his video live, but like I imagine during the video, he had done something like this for k equals 2. And then they're like, oh, for P2, I do this, but I do it over a range, but then it's different for the two. Okay, that's a cool speed solve technique, right? Actually, I don't know. I imagine it might just be as easy to like copy paste, and it's since been merged. But anyway, did I solve mine in 4 minutes? No, absolutely not. I wonder how long mine took to solve. I mean, I do have my personal times, so we know I solved part one in this and part two in this, so it took 19 minutes to solve part two. Part one probably took, I don't know, 10, 15. I'm not even close. If I'm honest though, I don't think one would use Rust if they were trying to speed solve. You'd probably want to use Python. Okay. Well, after looking at your solution, almost 6. What? 99 does not exist in 95 to 115? The what? Yeah, I don't. It may just be that they don't understand what the problem is asking. It that should be the case. Okay, we've talked about this enough. We've gone on for a while. Here's my solution. I'll post it. I'll also try and include the links. Hopefully, it was helpful understanding like there's two ways to solve this. I think it's just fun to think about other ways to solve it. It's clear that there's an even more mathy way to solve this. It looks like some people had looked at the input and found like even some more mathy ways to solve it. But I suspect the solution was meant to be something along this line right here, right? Can you do this? And maybe, you know, if you want to try to optimize it, can you do something clear to this? And I think if you're speed solving, it's going to look like this. And you probably don't even parallelize it in Rayon. You're just like, give me my stuff, get it done. Because, well, we could try and remove it and see how long it takes. So 20 milliseconds versus 6. Like that's when you're speed solving or whatever. That's not going to make much difference, right? So there's a potential for part two that it is. How does it change part? I mean, you're still under 100 milliseconds, so yeah, the parallelization is just like it looks like it's somewhere on the order of a factor of 4 that it's helping you. And again, the reason why it's that way is you're not doing a lot of like math in here. Where parallelization like super helps is if you're like, oh, I got to do Dijkstra's on a whole bunch of points on the grid. Then you can do Dijkstra in parallel, and now you're going from, a 2-second solution, or I've had it be like a 7-second solution to a 50 millisecond solution, just because you're able to like parallelize, um, you know, and heat up your room. Anyway, there you go. That's the day. I'd love to see your solutions. Again, feel free to post them as comments, or post them in Reddit, but just at me if you want me to actually look at them. Because again, especially for Advent of Code, much much bigger audience, and so it's going to be harder for me to see your solution in Reddit unless you like at me and I can see it. But I will look at it if you send me an ad. So um anyway, very good, very fun day. I'm excited. I love Advent to Code. And I don't know what else can you say about it. Lots of fun, lots of excitement. We'll see you for day 3 next time. Bye everybody.